Hello students, welcome back to JCE Connect series of lectures. In previous lecture, we have discussed about the Pelton wheel and its components and how to draw the velocity triangle for the Pelton wheel bucket. So in this particular session, we'll derive the equation for work done and efficiency of the Pelton wheel. For that we need to draw the velocity triangle, and from the velocity triangle we have to get the force exerting by the jet as well as the work done by the jet and efficiency of the uh, Pelton wheel bucket. Then for that, here I have drawn the plan of the bucket. This shows the plan of the bucket. So it has a hemispherical shape. So it looks like when you join two spoons together, and whatever the shape you get, so it will be like that. Then this common line, this represents the splitter of the bucket, and this one is the groove made at the bottom of the bucket. This is the groove, and this represents the width of the bucket, and this is the length of the bucket, and this is a stem which is to be connected to the uh, runner of the Pelton wheel. So just if you cut at this portion xx, so it looks like this. This is the section at xx. So here we get the central part, that is a splitter, and this is the uh, curved shape of the bucket, this and this. Now the inlet velocity, this is the inlet velocity triangle, which represents the straight line. Since the jet is striking the bucket at the center of the bucket, and that too at splitter, and it is striking tangentially, where alpha is equal to 0 as well as theta is equal to 0. So what do we mean by alpha here? Alpha is the angle made by the nozzle, and theta is the angle made by the relative velocity. Since the jet is striking the blade tangentially in the direction of motion of vane, hence alpha equal to 0 and theta equal to 0. Since alpha is 0, theta is 0, the velocity triangle will be a straight line. And when the velocity triangle is straight line, the AB represents the velocity of the vane, and BC represents the relative velocity relative velocity of jet with respect to the bucket, and AC represent the velocity, that is absolute velocity of the jet, which is equal to the whirl velocity. And in this at inlet, the velocity of flow will be 0. As you know, VW1 and VF1 are the components of absolute velocity. Since alpha is 0 here, then only you will be getting whirl velocity at the inlet, and the flow velocity will be 0. And remember, for a Pelton wheel bucket, the inlet velocity triangle will be always a straight line, because alpha is 0, theta is 0. If the jet is striking by making some angle with the horizontal, then you know how to draw the velocity triangle at the inlet. Okay, so otherwise the velocity triangle will be a straight line. Okay, this V1 is equal to VW1 here, and AB is U1 and BC is VR1, and this represents the angle of deflection here. So after striking the jet at the center, it get splitted into two parts equally. Then it will glide over the surface of the vane, and it exits. Okay, so as it exits, then if you draw this VR2 back, project it back, then this represents the uh, angle of deflection. This is angle of deflection. Okay, this is one. This angle is pi. That is 180 minus pi will be angle of deflection. Then you have to draw the VR2 in this direction, and V2, that is the velocity of the jet, which making an angle of beta, and here I am assuming the angle beta is less than 90 degree, that is acute angle. Then it is this is pi and this is also pi. This angle equal to this angle, and this vane also moving in this direction. Okay, it is rotating. Then this represents the U2. You can call it E, F, G and H. Fg represents the velocity of the vane and Gh represents the velocity of whirl at outlet tip. And this VR2 pi is the component of VR2 in horizontal direction, VR2 cos pi. Okay, whereas VW2 and VF2 are the components of V2 in horizontal direction as well as in vertical direction. So about the drawing of velocity triangle at outlet, so already it is been explained in previous lectures how to draw the velocity triangle at outlet, and it depends upon the angle beta. If angle beta is less than 90 degree, this is the velocity triangle at the outlet of the vane. If angle is 90 degree, then this V2 will be equal to VF2, where the whirl velocity will become 0. If beta is more than 90 degree, for that also we have seen the velocity triangle at the outlet. So once you have drawn the velocity triangle at inlet and outlet of the Pelton wheel, it is very easy to calculate the force exerting by the jet on the vane. Okay, so let's calculate the force exerting by the jet on the vane. So here in Pelton wheel, the jet strikes a number of buckets. So this Pelton wheel is striking by number of jet strike the number of buckets simultaneously, and the absolute velocity of the jet with which the jet strikes the bucket is given by, this is the absolute velocity. Okay, so actually the theoretical velocity will be root of 2gh, and I am multiplying here is a coefficient of velocity. So since there will be some losses, that is some losses, so which are to be taken into account, that is V1 can be given as Cv into root of 2gh, where h represents the head at the entrance to the nozzle. This h is at entrance to the nozzle, that is a net head. Then the Cv is the coefficient of velocity which takes care of the friction in the nozzle. Then the value of this Cv, the value varies from 0.9 to 0.98. And also the net head at the inlet of the turbine, which is given by Hg into Hf. As you know, I already explained in a layout of hydroelectric power plant. So this represents the gross head, that is the difference between the head race level and the tail race level is called as a gross head. That is a head of water available in a reservoir before it allows into penstock. Whatever the head is available, that is called gross head. It is difference between the head race level and the tail race level. And as the water starts flowing through the penstock, then it is entering into the turbine. So because of the friction in the pipe, there will be a losses, and after taking into account the losses, whatever the net head available at the inlet of the turbine, that is called net head H. That will be nothing, that will be equal to Hg minus Hf. Hg minus Hf will be the net head available at the entrance of the turbine. Now that is H can be given as Hg minus Hf, where Hf is a 4 FLV square by 2 GD. So this is the head loss due to friction, which can be calculated by using the Darcy's friction factor, okay, or Darcy-Weisbach equation. Then the velocity of wheel can be given as u equal to, so velocity of the wheel, because this is the Pelton wheel, or it is called as a rotor, which is coupled to the shaft. So these are the blades or the buckets or the vanes. Then the jet will be striking in this direction. Because of this jet striking the buckets, the bucket will receive the force, and this bucket transfers the force to the wheel, and the wheel starts rotating. As the wheel starts rotating, the shaft is also start rotating, and again the shaft is coupled with the generator, hence the production of electricity. This will continue. So here the wheel speed, that is u, is given by ku times root of 2gh, where ku is the speed ratio, and it is the ratio of wheel to the jet speed that will calculate in this derivation. So how we get the ratio of wheel to the jet speed, and here you remember this u, that is, as this vane is moving in this direction, u1 represent the velocity of vane at the inlet tip, and u2 will be velocity of the vane at the outlet tip. u1 equal to u2 equal to u. So as this u1 is equal to u2 equal to u, it is nothing but the velocity of the wheel only, because the force is being transferring from the bucket to the wheel. Okay, so for a small instance of time, this will move forward, then it takes the rotation. So u1 equal to u2 equal to u. So where ku is termed as the speed ratio of wheel to the jet speed, generally the value of ku will be practically this much, 0.43 to 0.48. Okay, practically it is to be taken this much, but theoretically the value of ku, which we get 0.5. But as the blade passage will be having a certain losses and all, so it has to be taken between 0.43 to 0.48. It has a friction losses and other kind of losses also. So to take care of that one, so generally the ku value will be 0.43 to 0.48. Okay. Then after this, you have to calculate the vane velocity at inlet. Vane velocity at inlet and outlet points of the vane. So as this is the vane, the shape, so this is the inlet point and this is the outlet point. So now you have to calculate the inlet velocity u1 and the outlet velocity u2. Then u1 equal to u2 equal to u here. Since it is a rotational, it is the wheel is rotating, so we have to take the rotational speed, that is pi dn by 60. Okay. Then where d is the diameter of the pitch circle or the rotor, it is called as a pitch circle or the rotor. This is called the pitch circle or the rotor or the disc, or it is also called as the impeller of the turbine. Where n is the speed of the runner in rpm, then the velocity triangle at inlet will be straight line. So as I explained earlier, it will be a straight line, and from the inlet velocity triangle, the velocity of whirl, the velocity of the whirl at the inlet is given by Vw1 is equal to V1 equal to Vr1 plus U1. So just look at this figure here. So velocity of whirl, that is Vw1, which is equal to V1, which can be given as U1 plus Vr1. U1 is the velocity of the vane and Vr1 is the relative velocity of the jet with respect to the bucket, and this Vr1 is nothing but the difference of V1 and U1. So if we want V1, it is nothing but U1 plus Vr1. Okay, since alpha is equal to 0 and theta equal to 0, where Vr1 is the velocity of incoming jet relative to the bucket. From the outlet velocity triangle, the velocity of whirl at the outlet is given as Vw2 is equal to Vr2 cos pi minus u2. So whatever the values were or the we are taking for the calculation of force, so it all depends upon this velocity triangles. So Vw2, this is the component of V2 in horizontal direction. This Vw2 is equal to Vr2 cos pi minus u2. Okay. So Vr2 cos pi minus u2. Also, the relative velocity at outlet is usually expressed as Vr2 to be taken k into Vr1. So this is the relative velocity. The jet will enter into the blade passage as a relative velocity, enters into the blade passage as a relative velocity, and again it exits. Since in a blade passage, if losses are present due to friction, if there is a losses due to friction, so this outlet relative velocity, whatever the velocity you are getting at the outlet, that will not be equal to Vr1 because of the losses. So that one, because of that, the Vr2 will be k times of Vr1, k times of Vr1. So what is this k? So where k represents reduction of the relative velocity due to friction. If the losses are neglected, suppose if the blade passage is assumed very smooth, if this blade passage is assumed very smooth, if there is no losses at all, if this blade passage is assumed smooth and the water is gliding over this smooth surface and it is coming out, then the Vr1 is equal to Vr2. In that case, the value of k will be 1. If any losses present because of the friction, then the value of k to be mentioned here. Okay. Then since the k represents the reduction of the relative velocity due to friction, if the losses are neglected, then the factor of k becomes unity. That is, value of k will be 1. Then the force exerted by the jet on a series of vanes. So here I am considering on a series of vanes. The force exerting by the jet on a series of vanes. And a series of vanes of the buckets in the direction of jet. Already we know this how to get. So in the impact of jet on a curved vane, a single vane, as well as the series of vane we have calculated previously, the same to be applied here. Okay, so here for a series of vane, this is a mass flow rate. Here I am applied impulse momentum principle. After applying impulse momentum principle, that is mass per second into bracket initial velocity minus final velocity, and the same equation we have been derived previously for considering the series of vane. Please refer that one, there you will understand how it has come. So force exerting by the jet is for a series of vane equal to the mass per second into bracket initial velocity minus final velocity. Then after simplifying you will get rho a v1 into bracket vw1 plus vw2. Why the plus sign here? Because the beta is acute angle or less than 90 degree. The work done per second fx into u, force multiply with the velocity of the vane. Then substitute the value of fx here, rho a v1 vw1 plus vw2 into u. Then also work done per second can be given as rho a v1. Then substitute the value of vw1 is nothing but v1, and in terms of vr2, that is vr2 cos pi minus u, this is vw2 into u. But vr2 is equal to what? K into vr1. So k into bracket v1 minus u1, because vr1 is equal to v1 minus u1. So can be substituted here. So here we can write v1 is equal to v2 equal to u. So assuming the inlet velocity, that vane velocity and outlet vane velocities are same. So rho a v1 into bracket v1 plus k times of v1 minus u cos pi minus u into u. Then simplify again, rho a v1 minus u plus k into v1 minus u cos pi into u. Then work done per second can be given as rho a v1 into bracket v1 minus u. Take the common v1 minus u out, then you will get finally 1 plus k into cos pi into u. Then after this, the efficiency of the jet can be given as finally, so we are interested in efficiency of the jet. So this can be given as work done per second divided by kinetic energy per second. It is output by input. So what input we are giving at the inlet of the turbine is kinetic energy of the water, that is jet power, that is kinetic energy of the water per second striking. Okay, so as we know the kinetic energy formula, half rho a v1 cube, because we know the kinetic energy equal to half mv square, but we want per second, then this is also per second. When you substitute, when you simplify this one, we get rho a v cube. Okay, so this is the kinetic energy per second at the inlet of the turbine. Then the output, as we know, that is the work done per second. Substitute here. After substituting, simplify this one. Then after simplifying, we get 2 times of u into bracket v1 minus u divided by v1 square into 1 plus k to cos pi. Okay, then for maximum efficiency, d eta by du is equal to 0. The differentiate efficiency with respect to the bucket velocity. So the efficiency depends upon the velocity of the bucket. We have to differentiate with respect to the bucket velocity for a given system. So this value should not be equal to 0. Okay, so take it out, then you have to differentiate only this term, then differentiate. Finally you will get, after differentiating, you will get the velocity of vane will be the half the jet velocity, or you can take the ratio of u by v. So it is u by v1 is equal to 0.5 we get, and this is represented as ku, where ku is called speed ratio. Remember, where ku is called speed ratio, as we earlier discussed, it is the ratio of wheel to the jet speed, and the value will be 0.5 as we discussed earlier. So look here, as I mentioned earlier, where ku is called wheel, that is the ratio of wheel to the jet speed. This is called as a speed ratio. Theoretically, we get the value of ku as a 0.5, but generally, practically, it is to be taken between 0.43 to 0.48. Okay, so the ratio of wheel to jet speed is termed as speed ratio. Okay, so I'll come back to this term, that is u by v is equal to 0.5. Okay, so how it can be taken into account in calculating the efficiency of the jet. So now theoretically what it says, the efficiency of jet will be maximum, or the Pelton wheel will give the maximum efficiency when the vane velocity or the bucket velocity is equal to the half the jet velocity. When the bucket velocity becomes half the jet velocity, then the efficiency achieved is maximum. Okay, so substituting this value in the above equation number 1, so this value, whatever the value we have calculated here, substitute in equation number 1, then what we get, so if we substitute this one here, then I substitute here and simplify it. So after simplifying, we get 1 plus cos pi divided by 2. Okay, just a substitute value of u here, then simplify it, we get finally 1 plus k into cos pi by 2 into 100. And what is the value of k? How to get this value of k? This value of k, it depends upon the smoothness of the blade passage. If the blade passage is very smooth, if there is no friction at all, then the value of k will be unity. If there is no friction along the vane surface, then the value of k will be 1. Otherwise, whatever the friction produces by the blade, you have to take the value of that one, then you have to substitute and get the efficiency. So eta max will be 1 plus cos pi by 2 into 100. For a semicircular vane, the pi value will be 0. Means if the vanes are like this, semicircular vanes, if the shape is like this, Okay, so if the deflection angle is 180 degree, means as the jet strikes, it glides over the surface and it is coming out of the blade passage like this, so it makes an angle of 0 here. So as the angle is 0 here, then we can call it as a deflection angle is 0 or 180 degree. When deflection is 0, then we get 100% of efficiency. This is only theoretically, but practically what happens, practically suppose as the jet strikes, if it is coming out by making an angle of 0 degree, okay, 0 degree, so as it strikes, it moves forward, but it will be holding certain quantity of water in the passage of the blade as it moves. Then it will release the water after moving, after going forward. It will release the water, whatever the water it is been releasing here, then that will uh, falls on the back of the bucket, so it will interrupt the movement of the bucket. So for that reason, so to this water should not fall on the back of the bucket, so it has to be fall away from the bucket. So that is the reason. So the angle, the deflection angle to be given as generally 170 to 180 degree, means whatever the jet strikes, so it has to go like this. It should not fall on the back of the bucket, which will reduce the speed of the runner. So instead of falling on the back of the incoming bucket, because the jet is striking here, so as it strikes, it moves forward. So when it moves forward, it will be holding certain amount of water inside the bucket. Then as it comes in this position, so it will release the water whatever it holds. Then if we are not giving any provision to release the water in proper way, then this will be falling on the back of the bucket, which will reduce the speed of the runner. So that's why the deflection angle will be given 160 to 170 degree. Then this angle will be generally 10 degree or 5 degree or 15 degree. So if it is 10 or 5 degree, then the cos 5 or cos 10 to be substituted here. So finally or practically the eta will be 96 to 99% we get. 96 to 99% we get the efficiency. Okay, so theoretically we assume the, or if we assuming the vanes are semicircular, for a semicircular vane the deflection angle will be 0 or 180 degree. For that we get 100%, but 100% we cannot achieve because of some practical problems. So we achieve the efficiency of wheel only 96 to 99%. Okay, I hope you understood this derivation. This is a very important derivation. And also one more thing, as I said, the value of Ku will be U by V equal to 0.5. Okay, the value of Ku. But what happens here, see, if you take the graph, this is efficiency and this is speed ratio, U by V. If you take this one, okay, see, if suppose this is the impeller, rotor, these are the bucket, okay, jet is striking. If this jet is buckets, this is stationary. If these buckets are stationary, then the velocity will be what? 0. When the velocity is 0 here, velocity of the vane, is if these buckets are stationary, then the velocity of the vane will be 0. When the velocity of the vane is 0, what about the efficiency? Efficiency is 0. Okay, efficiency will be 0. Then also, if velocity of jet is equal to velocity of vane, if velocity of jet is equal to velocity of vane or velocity of bucket, if both are same, this jet may not strike the vane, because both are moving at the same speed. It may not strike the vane, hence there will not be any rotation, hence the efficiency is also 0. Try to understand, when the vane is fixed or when the vane is stationary, there will not be any efficiency. Also, when the vane velocity is equal to the jet velocity, this is jet velocity and this is the vane velocity, and both are equal, this jet may not strike the vane. In that case also the efficiency will be 0. Hence we get efficiency here. But when we get a efficiency maximum, when this ratio is 0.5. So this is 1, this is 0, and this is 0.5. So 1 means when u will become v, other one is when u equal to 0, and other one when u equal to